So today we're going to talk about Amitsur's theorem. This theorem gives us a description of the kernel of the restriction map on the Barrow group. So let us first describe the restriction map. So let's say X is a variety over K, then we have a natural injection from K into the function field of X. This will induces a map on the Barrow groups by functoriality. We call this map the restriction map with respect to X. Now, we want to give an explicit description of this map in terms of Savary-Barrow varieties. So, remember that we have a correspondence between Savary-Barrow varieties and central simple algebra. So, given a Savary-Barrow variety Y, we can think of it as a class in the Barrow group by thinking of it as its corresponding central simple algebra. The map will send the class of Y to the class of the fiber of Y over the function field Kx. That is why it's called a restriction map. We're restricting Y to a fiber. So the Amitsur theorem is going to give us a description of this kernel. We'll do the proof in another video, but for now, let's just observe why the kernel of this map must contain X. So why is that? Well, I should note that that's only in the case when X is a Savary-Barrow variety. Otherwise, we cannot even view X as an element in the domain, right? So let's have a look at what is the image of X. So the image of X should be the fiber of X over the function field Kx. But this fiber splits. So why does this fiber split? Because this variety contains a Kx rational point, namely the generic point. Here we are using Chatelet's theorem. Remember, Chatelet's theorem generalizes the fact that a conic is rational if and only if it contains a k-rational point. This is because if a conic has a rational point, then we can use stereographic projection from that point to create a map from the conic to P1. Now, more generally, any Savary-Barrow variety over a field L splits if it contains an L rational point. And in our case here, we are looking at this taking L equals to Kx. So we see that every Savary-Barrow variety X must split over its function field Kx because it always contains a Kx rational point, namely the generic point. So the kernel of the restriction map always contains X. Now, before moving on to the proof of Amitsur's theorem, let us discuss a corollary. This corollary basically says that the subgroup generated by X inside the Barrow group is a birational invariant of X. So if X and Y are Savary-Barrow varieties that are birational, then they must generate the same subgroup inside the Barrow group. And why is that? Well, if X and Y are birational, right, which means by definition Kx is equals to Ky, then the two restriction maps are actually just gonna be the same because the restriction maps is just a map of taking fiber over this function field. Right? So they are actually the same. So Ry is equal to Rx, but Amitsur's theorem said that these subgroups are just the kernel of the restriction map. So if the restriction maps are the same, then these two subgroups are also the same. So if X and Y are birational, then they must generate the same subgroups inside the Barrow group of K. And thus the subgroup generated by X inside the Barrow group of K is a birational invariant of X.